Alright kiddos, good morning. Happy snow day. Hopefully you have a nice relaxing day with a little bit of math, a little bit of learning involved. So I think it's time we moved on, and you guys did a great job of the verifying of trig identities. Um, and the next step is solving trigonometric equations. And so what you'll notice with these equations, and I've listed some types below, is that instead of a variable being x or y, the variable is the sine of x, or the cosine of y, or the tangent of x. And so we have some strategies that we have to employ, and I'll outline each one in particular as we go through it. So here we go. First of all, we're going to solve each of the following and on a particular interval, right? Recognizing that there are probably, of solutions, there are probably going to be an infinite number of them, right? Because of the cyclical periodic nature of these functions. So usually we're given a specific interval over which we're going to find the solutions. Okay, so let's take a look at the first two. And the first two fall into the category of just solving directly, right? Using ultimately either the unit circle or trigonometric inverse functions, the arc sine, arc cosine, etc., etc. Okay, so the first one, what I'm going to do is I'm going to treat sine of x just like I would an x. So I'll subtract 1 from both sides. So I get 2 sine x equals -1. And then I'm going to divide by 2, right? Just like you would if we were solving 2 times x plus 1 equals 0. So we end up with that particular equation, right? And so once I've chiseled away at the sine of x, which I treat like the whole variable, now is the time either to think about the unit circle or to use my calculator to find the inverses. So I'll use the unit circle here. And so recall that the sine is the y value of the terminal point, so I'm looking for terminal points that have y values of -1/2, right? And so therefore I'm looking at really the third or fourth quadrants, right? So here, there's my -1/2, and here's another y value, -1/2, right? And so therefore the angles I'm looking for are 210, or 7 pi over 6, or 330, or 11 pi over 6, right? This nice unit circle is thanks to Wikipedia, right? So therefore on the interval 0 to 2 pi, my solutions are x equals either 7 pi over 6 and also 11 pi over 6, right? Or in terms of degrees, 210 or 330. Again, those are just the two values x, right? That's what we're solving for, the angle for which the sine of that angle is -1/2, right? So in this particular example, I'm solving directly using inverses, subtract 1, divide by 2, and then I use my understanding of the unit circle to solve for x being the angles on this interval 0 to 2 pi that satisfy this original equation. Okay. The second one is very similar, however the numbers are a little messier, so if that is indeed the case, we're going to solve in a similar fashion. I'll subtract 0.2 and divide by 0.4. Right, so your first step would be 0.4 sine x equals 0.3, and I'm going to divide both sides by 0.4, so basically we get 3/4, right? Okay, so now the one thing to consider is that, well, there is going to be solutions because the sine of x, remember, ends up being between -1 and 1, and 3/4, just like -1/2, is on that interval -1 to 1, falls within the range of the sine. So therefore there are going to be some angles, or an angle, for which the sine of that angle equals 3/4. Now that's not a nice number, right? It's not 1/2 or √2 over 2 or √3 over 2. It's not a sine value for those known friendly trigonometric angles. So therefore what I'm going to do is use my calculator, right? So my calculator, I'm going to turn it on. Snow day is fun, that's correct. And so if I'm trying to figure out when the heck the sine of x equals 3/4, I'm going to take the inverse sine of both sides, right? And that is also referred to as the arc sine. So it's the inverse or arc sine, which looks like sine to the -1 of x. I'm having a hard time figuring this out right now in Google Docs. So I'm going to take the inverse sine of both sides. Sine, I'll just say to the -1, fair enough. Where's the caret? Oh boy. Here's a to the -1 of x. And I'm going to, of the sine of x on the left. And then sine, the inverse, the arc sine. We use this to find angles during the SOHCAHTOA bit, if you recall, of 3/4. Of course, the inverse of the sine of x, by definition, is x. And on the right, I just need to evaluate what the heck the inverse sine of 3/4 is, right? So if I'm in, well, you know what? Let's go back to degree mode. Well, let's check what mode I'm in. I want to make sure I'm in radian mode. Okay, I'm going to get rid of that nonsense. And I'm going to take the inverse sine, which is second sine of 3/4. Okay, and that gives me in radians this particular value. If I want it in degrees, maybe that makes a little more sense in degrees. Again, I'll take the inverse sine of 3/4, and there's my 48.59 degree angle. So let's just think of it in terms of degrees. Might be a little bit easier. So 48.590 degrees. Okay, now that's what's called the principal solution. But if you understand a little bit about the unit circle and what the sine and cosine come from, or where they come from, we know that there's probably going to be another value. So the question is, where is that other solution or other solutions between 0 and 360? So if we're looking for a positive sine value, right, then the only options are quadrants 1 and 2, where the y values are positive. And we want the sine value to be 3/4. So note that the sine of theta is equal to the sine of 180 minus theta, right? So to get the other solution, I'm going to subtract that 48.59 from 180, and that ends up with what, I'm not sure what the heck that is, 180 minus 48.59, and that's going to give me the second solution, 131. 0.1 degrees, and those are my two solutions, 131.1 in degrees and 48.59 on the interval 0 to 360. Okay. Next type. Okay, so 1 and 2 are you solve directly, and either if it's a nice number like 1/2, for which we know the angles, you can use your understanding of the unit circle, or if it's not a nice number like 3/4, we use the calculated inverse sine in this case. And then we kind of think about, well, is there another angle that also, in addition to the principal solution which our calculator gave us, will also have the same sine value? And for that we use some identities or just a basic understanding of the unit circle and how it works. Okay, the next couple we're going to kind of work more algebraically, and so going to some of these other strategies, we can factor, we can substitute trig identities. So here we go. Let's look at this particular problem, right? And in fact, you know what? I'm going to save this one for either next video or class on Tuesday. But let's forego this. It's really just asking what is the sine of x equal to cosine x. So I think the easiest way to solve that one is to think it through. But let's go to some more factory types, right? Like actually most of these are. Okay. So let's get our algebra on and let's examine the first one. Okay, I'm going to treat cosine of x like a variable. I have a cosine x, not an x, cosine and x, both of which are factors of that, right? So one thing I can do is I can factor out, I'm going to think about cosine of x as a variable and factor out cosine of x from both pieces, right? And what I'm left with here is 2 cosine x, and what I'm left with here is just a root 3. Oh, I'll just write it root 3. Okay. Right, so just as it were 2x squared minus root 3x equals 0, you would factors to get the product of something equaling 0, right? And then as we would with a polynomial, we'll set each factor equal to 0, right? So cosine x equals 0, or 2 cosine x minus root 3 equals 0, right? So just as if these were polynomials, if a times b equals 0, that means either a has to be equal to 0, or b has to equal 0. Right? And now I'm going to solve each one individually. Right? The first one is pretty easy because 0 is a nice number. We get to one of those quadrantal angles, or 2 of them in fact. And so based on the unit circle, if you don't remember the zeros of the cosine of x equals 0 at pi over 2 and 3 pi over 2. Okay, if you don't remember that, look at the unit circle, right? X value of the terminal point, we want to end up here, pi over 2, 90, or here, 273 pi over 2, right? X value 0, X value 0. Okay? The second equation is a little harder to solve, but nonetheless ain't so bad. Right? So now I'm just going to subtract or add root 3 to both sides and divide by 2. Right? I'm isolating not x but cosine of x. Add root 3, divide by 2. So what I end up with is cosine of x equals root 3 over 2. Okay? Oh, okay. Whoops. Root 3 over 2 is one of those nice values for those nice angles. So, okay, I remember when the cosine of x equals root 3 over 2. Remember, it's the x cosine of x of the terminal point. So, oh, there we go. There's a root 3 over 2. And once again, not in the second, not in the third, but in the fourth, oop, there's another root 3 over 2. All right? So my two solutions based on the unit circle are going to be pi over 6, or 30. Oop. And also that same essentially reference triangle, reference angle in the fourth quadrant. Root 3 over 2 is 11 pi over 6. Okay, so this particular has 1, 2, 3, 4 solutions on the interval 0 to 2 pi. Okay, here's another factorable trigonometric equation, right? So a general strategy is, well, if that were a polynomial, I'd set it equal to 0, right? So I'll do that. So sine squared, of x minus sine of x minus 2 equals 0. Well, that's what I would do if this were x squared minus x equals 2. I'm going to follow a similar pattern, right? Now I'm going to factor it, but instead of, it's a quadratic, but not in terms of x, but in terms of sine x. I put my sine x here. I put another sine x here. Right, and this is very similar to x squared minus x minus 2 equals 0. So I would ask you, how would you factor this particular quadratic? Well, you're looking for two numbers that multiply to be negative 2 and add to be negative 1, right? So that's going to be negative 2 plus 1. Right, so this is quadratic in terms of not x, but in terms of sine of x. Right, so I've factored this trigonometric quadratic in the same way I would factor this polynomial quadratic. Right? And so now all that's left is, just like I did in the last problem, set each factor equal to 0 and solve individually, just like I would this one. Right, you got x plus 2, x minus 2, x plus 1, then you set each one equal to 0 and solve. But in this case I have sine of x plus 1 equals 0. Or the other factor, sine x minus 2 equals 0, right? Now something kind of cool happens here, or easy I should say. Right, this is easy to recognize. Sine of x equals negative 1. Go to my unit circle. The sine is the y value of the terminal point, so this is the only point from 0 to 2 pi I want to land at. So there's pi, x is pi, or 180 is the solution. Right? And then the other particular factor, sine x if I add 2 to both sides, well, that never happens, right? Right? Sine x can only be at most 1, right? So if this number here is outside of the range of the sine function, there's no solution that comes from that particular factor, right? So therefore, the only one solution for this particular quadratic, which is quadratic in terms of sine, is pi. Okay? There we go. So that's enough for today, right? What I'd like for you to do is think about solving these two, number 6 and 7, okay? And I would give you the suggestion that for number 6, I would rewrite sine squared using the Pythagorean identity as 1 minus cosine squared and work from there. And for this one, I would also substitute our sine of the double angle identity, 2 sine x cosine x. Okay, and then factor, right? So for these two, I want you to try. Substitute an identity. I would go here, and I would go there. And then factor, if necessary, and solve from there, as I did in the preceding problems. Okay, good luck. Perhaps I'll see you tomorrow. Text or call or email with any questions. Bye-bye.